In these sequence of videos, we are going to introduce you to the bootstrap technique. The bootstrap is not a model, contrary to some opinion in some quarters. It in fact is a method. It's something that sits on top of a model. And we're going to be using the bootstrap technique to actually try and find out whether a particular method, in particular the Mac method, does it work. We're also going to be testing optimal identified PTF models to see if they work and contrast the two, an optimal PTF model with the Mac method. Now, the bootstrap originated, it is a resampling technique. It was popularized by Brett Efron in 1979 in his celebrated Annals of Statistics paper. Efron drew our attention to its considerable promise and gave it its name. Somewhat unfortunately, the name bootstrap conveys the impression of something for nothing. It's like, you're sort of idly resampling from your sample, presumably having about as much success as sort of pulling yourselves up by your bootstraps. The technique is used, but in fact, you do get almost, you do get more out of your sample by bootstrapping. The bootstrap technique is used to calculate standard errors of parameters, confidence intervals, distributions of forecasts, and so on. Typically, it is used when the sample size is small, so that you can't test any you can't make and test any distributional assumptions. They can't be tested. Or asymptotic where asymptotic results will also not be applicable. Even for large samples where you can test distributional assumptions, the bootstrap might still play a useful role, especially when you need to find the distribution of a particular statistic, a particular function of the data, but the mathematics becomes quite intractable in terms of determining the distribution of this statistic. Now, what's the MAC method? The MAC method is a regression formulation of volume-weighted average link ratios, and we do, even though we have explained this method before, how you formulate link ratios as regression estimators, whether it's arithmetic average, volume-weighted average, or any other type of average. We are going to explain again the part of what's called the extended link ratio family modeling framework, where the MAC method is the default starting model. Now, we use bootstrap samples. Bootstrap samples are supposed to replicate the features in the real data, and if they don't, if the features in a bootstrap sample are very different to the features in the real data, one would then argue that it's the method or the model that is inappropriate for the data, that the method itself has not replicated the features in the data. Because after all, bootstrap samples are the kind of samples you would argue, this is the sample I could have observed, but this is the real data, but I could have observed this sample, sample 1, bootstrap sample 1. This is my real data, but I could have actually observed bootstrap sample 2, and so on. Okay. So the main goals are to show, let me just get rid of some of this. I must have been played with this before, let me erase it. The main goals are to show how bootstrap samples are generated, explain the MAC method and related methods, other derivatives of the MAC method, how bootstrap sampling can be used to test the MAC method, compare bootstrap samples with the optimal PTF model bootstrap samples. And I think you'll find that bootstrap samples based on the optimal identified PTF model look very much like the real data. Bootstrap samples based on the MAC method do not. You can immediately distinguish between the real data and bootstrap samples based on the MAC method. Okay, let's just look at a simple illustration where you might use the bootstrap. You have a random sample of observations, y sub 1 to y sub n. It's a small sample. You can't test what distribution the data come from. whether it's log normal, Pareto, whatever else. So what you do is you just calculate the sample distribution function. That's all the information you have. And you calculate the 90th percentile, and but you don't know the error rate. You don't know the standard deviation of 90th percentile. So what you could do is create bootstrap samples of the original data. Now when you do that, you're making a basic assumption. These observations all they're independently distributed from the same distribution, from the same population. So we put them all inside a flask. We take one at random out of a flask and call that Y1 star. That's your first bootstrap datum. You put that one back in the flask, draw a second one at random, call it Y2 star, until you've got Y star sub n. Okay? Now, in this particular bootstrap sample, you might have some repeated measurements because you are resampling by replacement. So, and you calculate your 90th percentile, will be very different based on the original data, and you can generate bootstrap samples a number of times, and this will give you an idea of the error rate in the 90th percentile. So the underlying idea of the bootstrap is you don't know the distribution of the observations, and parametric distributional assumptions cannot be tested. In simple cases where observations come from the same distribution, the best estimate of that distribution is the sample distribution function, which we just showed you that. We worked with that. Okay. What if, in fact, you have a triangle? Well, when you have a triangle, you can't argue that all these observations come from the same distribution. In fact, the first example we look at in the next video is just bootstrapping this sample and assuming that all these values in the different cells all come from the same distribution. Of course, that's a very silly assumption. And when you create that particular bootstrap sample, an observation that sits there might be reallocated there, an observation that sits there might be reallocated there, and then you'll see that your bootstrap triangle is very different to the original data. So that's a silly thing to do. So you cannot, it doesn't make sense to bootstrap the original sample if the sample values do not come from the same distribution. So you need a model. So let's create a model. So what if each observation does not come from the same distribution? You let y sub I have a mean mu sub I with an error term. So this is a linear model. You would then fit the mu sub i's. No distributional assumption about the error term epsilon I. You're not going to make a distribution. Incidentally, if you do make a distributional assumption and you test it, you actually test that distributional assumption, and it's not invalidated. The bootstrap technique, if you use it properly, will give you the same answers as the parametric model. So there's no need to use it because you could do everything through the mathematics. In fact, that's what we do in PTF anyway. You're assuming that the standardized residuals are assumed to, well, they are random from the same distribution. Residuals are sampled with replacement. Okay, but that's an assumption. So bootstrap samples versus the real sample, the data. If the model is correct, a pseudo sample, the bootstrap sample, should have the same characteristics as the real data. A bootstrap sample and the real data are indistinguishable in respect of the trend structure and volatility about the trend structure. They should be having the same characteristics. Bootstrap samples from the MAC method and related methods versus bootstrap samples based on the optimal PTF model. Bootstrap samples to the data based on the MAC method and do not reflect features in the real data. We'll do a few examples. You can easily distinguish between the real data and the bootstraps. However, you can't distinguish. It's very difficult between the bootstrap samples based on the optimal PTF model. We're going to look at two LRBs that we studied before. One of them is ABC, where there's a major trend shift along the calendar years, a couple of trend shifts. And the other one is LR high, where there's a number of calendar year shifts, but there's also heteroscedasticity versus development years. In other words, the variance of the normal distribution changed by development year. So in both cases, you'll find that samples based on the MAC method, bootstrap sample, are very different. Very different. They look very different to the real data. In this particular example, link ratio high, LR high, we also find that the MAC method gives a reserve answer, which is about twice the reserve that you should be holding. About twice the reserve that you should be holding. So both data sets are real. They each have calendar year trend changes. The second one, number 2, also has a change in process variability versus development year on a log scale. ABC doesn't have a change in process variability, but it does have distinct trend changes along the calendar year that the MAC method can't pick up, quantify, and so on. Okay, so we have data, we have a model, we therefore also have, we fit the means. We then argue, we are saying that the error terms do have a distribution, often with, a distribution with mean 0, often with the same variance. We calculate the residual, which is the observed minus the fitted. Remember, residuals represent trend in data minus the trend estimated by the method. So the mu I depend on some parameters. The epsilon I are called error terms. So usually the volatility of the data around the trend structure. The trend structure is represented by mu sub I, and these are the variances of the error terms which form an integral part of the model. That's part of the model. Most importantly, the model assumes that the standardized errors are random from a single distribution with mean 0. This should also apply to the standardized residuals. The residuals are estimates of these errors. Okay, but the errors are part of the model. So let's write down our residual again. The residual is the difference between the observed and the fitted. Residuals represent the trends in the data minus the trends estimated by the model. You can also calculate the standardized residual, which depends on the standard error of the residual itself. And what you can do now is you know that an observation equals a fitted value plus a residual. Or if you like, the residual equals the observed minus the fitted. Now the residuals are assumed, this has to be tested, they're assumed to be structureless in the sense they're all random from the same distribution. You put them into a flask, you select one at random, let's call it E1 star, comes out of this flask at random, E1 star. It might be the residual of the fifth observation, Y5. And then you apply that residual, scaled, possibly scaled, to the fitted value, to the first fitted value, and this results in the first bootstrap datum. Then you put that one back inside the flask, select the second one, E2 star, select E2 star, apply to the second fitted value, and you get the second bootstrap datum. So you kind of work backwards. You're assuming now that the residuals are random. The observations themselves all come from different distributions, but once you adjust them from a different mean, you're assuming that the error term all comes, or the residuals all come from the same distribution, so you bootstrap the residuals rather than the original data, because the original data doesn't come from the same distribution. Okay. What about for a triangle? We have a triangle of values, we have fitted values, we have residuals. We put all the residuals into a flask, and then we create a bootstrap triangle of residuals. So, you take one at random, put it there, put it back in the flask, select another one, put it there, and so on, until you work for the whole triangle. So you got a triangle, bootstrap triangle of residuals. You then add those to the fitted values to create a bootstrap sample. So typically people who use the bootstrap on the MAC method, actually there's another issue. They don't really bootstrap the MAC method, they bootstrap another model, which is really a different model, but that'll be part of a different video. So if you were creating lots of bootstrap triangles, because you can repeat this procedure many times. You would then apply the MAC method to each one of the bootstrap triangles. Every time you apply the MAC method to each one of the bootstrap triangles, you get a different answer. There's also a way of also adding sort of process variability and so on. And then this way you can calculate the distribution of your reserve forecast. Okay? All right. Well, let's look at a simple example. I guess the simplest example is when we look at triangle ABC, where we just bootstrap the triangle itself. And we find out immediately that the bootstrap triangle doesn't look anything like the original triangle because we allocate values in development year 7 to development year 1, 0, 2, and 3, and so on. Okay. The next example is just based on fitting two straight lines. So let's suppose you've got some data which you generate using two straight lines. So it's random data around two straight lines, and it looks like this. And now, after generating the data fitting using two straight lines, you actually fit the two straight lines. You calculate the residuals. These are the residuals. You put them all on the x-axis. Incidentally, this PowerPoint display is available on the website. So if you're just before you watch this particular video, you would have read the script, the abstracts of the different videos, and you'll see that there's a link also to this particular PowerPoint display. So now you're going to reshuffle the residuals on the x-axis, on the horizontal axis. You can see where we shuffle them. I shuffle them again. Just shuffle them around a few times. And now we take the bootstrap residuals and add them to the fitted values. The fitted values set on the two lines. And now we've got new data, which is the light blue. Of course, you have to rescale the residuals. That's a bit of a technical issue, but anyway, you've got it. You've got the ideas. And so this is now my bootstrap sample, one bootstrap sample, based on the fitted model. And this is the real data, the dark blue. And now you create many bootstrap samples. And to each bootstrap sample, you fit the two lines. Don't worry about this part. I don't know what that appears. Something to do with Excel. It actually should be just two straight lines. And you can see that the lines going up to about period 6 are pretty much close to each other. The lines starting at around 6, 6.5 are pretty close to each other. Okay. But also instead, you fitted the wrong model. In other words, one straight line. Okay, what happened if you fit a singular regression model, one straight line? When you calculate the residuals now, because there are two trends, you've calculated the average trend. So the average trend is higher than the trend in the earlier periods, but it's lower than the trend in the later periods. Residuals represent trending data minus the trend estimated in the method. So they look more like this after we scale them. They have a negative trend, followed by a positive trend. So for the early periods, up to about period 6, the average trend is larger than the trend in the actual data. Beyond period 6, the average trend is lower than the trend in the data. Now, what if we bootstrap these residuals? Oops, we've done that. And if we fit one line to the bootstrap samples, we go from there to there, you just get one line. But what if we fit two lines that intersect at around 6? Well, you still just get one line. There's no change in trend. So now you could see that the bootstrap samples are not the same as the real data because the model was not the right model. One single line was not the right model. The data was generated by two trend lines. And this is the idea we actually use in finding out whether a method works. If a method works, the bootstrap samples or the bootstrap triangles have the same trend structure and the volatility around its trend structure about the data. Because we'll find later that I want to go back to the first slide. Go a bit faster. No, we'll find it. Oh yeah, there it is. ABC on the log space and log scale only has trend structure, little process variability. This has trend structure plus variation in process variability, the variance of the normal distribution versus development periods actually changes. And you'll see that the residuals based on the MAC method just can't capture that. So the MAC method for this triangle group, for this particular triangle, does not capture two features of the data, the trend structure plus the process variability around the trend structure. Here, you'll find out that it doesn't capture any of the trend structure at all. Thank you.